So camera's not working today. I'll get that fixed for next time. So last day, the example we worked through at the end of class was this more realistic scenario where you have one group and you've got a generative model for the data such that you're uncertain about where the group's mean is, and you're also uncertain about where the group's variability, like how variable the group is. And I guess to put that more accurately, you're uncertain about where the population's mean is, and you're uncertain about what the population's variability is. You have a sample in your hands, and you can compute its mean and its variability, but you want to make inference or do inference from the sample you have to talk about your beliefs about the population. So load this up. I'll generate some data, package the data for Stan. I'm going to open up my files here and open up that Stan file and pull it out into its own window. So again, just reviewing our Stan code, there's 3 sections: data, parameters, model. The data, we tell it, okay, there's a vector of observations y, there's this many items in y, and so we have to tell it what that number is in the first place. We have our model down here, the part where the data is on the left-hand side of the squiggle. It's the part where it's sort of expressing how we think the data was generated. So this is the generative model part. So we think that y was distributed, from a normal distribution, a population that's a normal distribution, with some mean and some standard deviation. Both of these are just sort of variables, so that implies that they are unknowns that we want to do inference on. So we have to tell Stan what the unknowns to expect down here in the model area are in the first place up here in the parameters area. So mu, it's a real. It can take any number on the number line, including negatives and decimals. Sigma, on the other hand, that's the standard deviation of the normal. So we know that that needs to be sort of bounded by 0. You can't have negative variances or negative standard deviations. So that's what this little bit is on the definition of sigma. As in our earlier examples, we decided to, or whenever you have an unknown, you have to express what sort of your prior beliefs about that unknown variable are. And we use a normal distribution to sort of define the shape of our beliefs such that we'll have a sort of peak belief at 100, but our beliefs are going to taper off in sort of a gradual way on each side. And we decided that 20 was a good value for describing how our beliefs would fall off on either side. So a normal distribution with a mean of 100 and a standard deviation of 20 sort of had a nice shape that characterized our beliefs about where the mean of the population might be. And for this variance or variability parameter, sigma, we decided that we wanted to use a log normal distribution that sort of is a normal distribution but on the log scale. So since it's on the log scale, we have to put numbers here on the log scale. I think we decided that we wanted it to be centered at a real value of 15, which is about 2.7. Whoops. And we wanted it to have a variability of about, I don't know, what did we decide? Let me actually see. What is exp2? So that's, if on the log scale it's 2, on the real scale it's 7. And I'll validate on the log scale. If it's 2.7, that's on the real scale about 15, so that's good. So why don't we just leave it at 2? It might be a different number than we used the other day, but this is, again, a distribution where it's got a peak at, on the real scale, 15, but it tapers off on either side. It's slightly skewed, and it has a sort of a positive domain. It's only defined in the positive values. So these two, again, sort of reflect the shape of our prior beliefs, having not seen any data. This last line establishes our generative model for how the data were generated, and we give it our data. So this is our stan file, having sort of decided, okay, these are the beliefs that we want. We can save it, switch back over to our R, and again, I actually re-downloaded this from the GitHub site, so I need to delete all the stuff that I had you delete the other day. I'm going to double check that I'm in the right working directory, 02. Yep. So the this line, if we run it, it's going to start compiling that stan file. If we'd made any mistakes, they would come up right away, but since it's waiting for a little bit, I can tell that we haven't made any mistakes, and so it's compiling it. And having compiled it, while that goes, I'm going to talk about what the next little section is. Having compiled the model, we're now going to run a function that combines the model with our data. I'm actually going to delete a whole bunch of these arguments here, just to sort of make it clear what's actually going on. So we're gonna create a new object called out, and in it we're gonna put the result of this call to a function. So this function, it's the sampling function that's located in the rstan package. We've got 3 arguments: object, data, and seed. Object, that's just the thing that we just created up here using the stan model function. It's sort of a reference to the compiled stan model. Data is whatever data we sort of prepared to give to stan. And this last thing, seed, that's recommended because what this stan sampling is doing, it's doing something a little bit random. And so you want to set the seed. Setting the seed means that if you come back a few days later and run this on the same machine, you'll get the same results. Now, a little bit annoyingly, if you run this on an entirely different machine, so I've got a Mac here, if I were to go and run it on a PC that has a different CPU in it, it might get slightly different results. Ideally, I'll show you how to run things such that you're sort of pretty certain to get the same result regardless of what computer you're on, but it won't be precisely the same result. You're going to be trying to aim for at least sort of the same result within a few significant digits. But as is, I'm giving it 3 arguments: object, data, seed. And what's going to happen is something behind the scenes that's quasi-random is going to happen. It's actually going to do the same thing 4 different times, each time starting at a different point in sort of random search. But this is such a simple model that it goes so fast that you pretty much can't see the progress, but you'll see sort of 4 chunks of numbers go by. And when it's all done, you can print a summary. I'll actually make this window bigger so the print looks better. So, and we get the summary table, which we walked through the other day, but I'll walk through again quickly. It just tells us sort of how many times we tried to do inference. That's the 4 chains, so that's default. If we wanted to change the number of chains, that's the chains argument. 4 is good. My computer here has the ability to do, well, I guess it's a good idea to do multiple chains to make sure that whatever you're doing, so there's 2 aspects of the randomness that's happening inside this function. One aspect is it starts, well, let's say, imagine that you're on a boat in a lake and you're trying to characterize the shape of the bottom of the lake. But you have rules about how to move the boat from one place to another. I won't tell you about those rules. They're designed to make sure that you sort of optimally characterize the bottom of the lake. But you have to start somewhere. And if there's some randomness in those rules, it may be that you started in a weird place and that led to the final result being a little bit weird. So it's a good idea to start at multiple different random places across the lake. So that's what having multiple chains does, is it says, okay, do the same thing over multiple times, starting at different places. So a typical sort of check to make sure. So if you only did one, you may have started in a weird place. So good idea to do more than one. So how about two? Well, maybe there's a sort of a less likely chance that those two places are both weird. So usually you'll see four, because before the last couple of years, most computers could do at most 4 things at a time. But I have 8 cores on my computer, so I can do 8 things at the same time. So I usually put this up to 8. Now, the way it's set right now, it's actually not going to try to do all the chains at the same time. It's going to do them one after another, as you see here in the output. If you have a multi-core computer, like I think most computers are these days, you can actually tell it to do, come on, there we go. You can tell it to use all of your cores. So if I say cores equals 8, and I ran this, it would run 8 chains all at the same time instead of one after another. This is only really going to matter, this bit is only really going to matter if you, once we get into more complicated hierarchical models that take a long time to compute. Something like this, where each chain is getting done in about 30 milliseconds, it's actually going to be slower to try to tell it to do them all at once, because there's overhead in trying to set up the processes in parallel. So for the first bit, we'll not bother with that. And we'll actually, the default number of chains is 4, and that's going to be fine for now. So that's why I had us just with the accepting the defaults of serial chains and 4 chains in serial. So that's what this little bit is telling us. There are 4 chains in serial. Now there's a bit with each chain having iter 2000. So there's an argument to sampling called iter, and the default is 2000. And this determines sort of within each chain, once you've started in your search of the lake bottom, how long do you spend searching? Generally with these simple models, 2000 is plenty. I'll show you, if you look in the output of this, to determine whether you've searched sort of long enough, the 2 last columns here, NF and R hat, are the ones you want to look at. R hat you want to be equal to 1. And NF, I like to make sure that that's about 1,000. So here, I actually do see that R hat is equal to 1, and NF is, they're all above 1,000. So I've searched long enough. If I actually tell it to, let's see, iter equals, let's just say 100, and I'll say chains equals 2. So if I only do 2 chains and 100 iterations on each chain, and look at the output now, it'll show that R hat is not 1, it's above 1, and NF is not 1,000. In fact, they're very small numbers. That means that I likely haven't done enough effort in searching the lake. I haven't spent enough time searching the lake. So I wouldn't sort of want to trust the numbers in this table very much. So let's try bumping it up to 4 chains. What does that do? That starts at different places. At the end, so this NF goes up because it's actually combining the information from the different searches. And R hat has gone down closer, but NF is still not very big. So what if I bump this up to 200? Okay, getting better. R hat's getting better, and ditto the number of effective samples is getting better. Let's bump it up to 1,000. Okay, we're getting, so r hat's pretty much 1, and the effective sample size is also pretty much very high now. So that would be great. The default is 2,000 iterations, so I can just, again, leave that for these simple models. The default of 2,000 iterations is usually going to yield enough sort of sample effort to have these as above 1,000 and this one as 1. So having achieved r hat of 1 and effective sample size for all the parameters of greater than 1,000, or values in this column of greater than 1,000, I can actually look at what this table actually is. So it's got 2 rows, 1 row for mu, 1 row for sigma, and that's describing the posterior distribution for these two variables. So remember, the posterior distribution reflects what is the sort of shape of what I should believe once I've taken my prior beliefs and updated them with the data that we just observed. So the prior belief for mu was centered on 100 and had a variability of, I think we had it as 20. Double check. Yep. Now it's a distribution. It might be normal. We'll have to actually visualize it. But it's got a mean at around 110. The median is, again, actually way over here at the 50th percentile. That's what these columns are. The 50th percentile is also 110. So the fact that the mean and the median are the same kind of suggests that it's a symmetric distribution. This column, SE mean, you can pretty much ignore. This column, though, SD, this is the variability of our posterior distribution. Now, our prior distribution had a variability of 20. And remember the other day I said that you can think of the variability of your prior distributions as reflecting sort of how certain you are or uncertain. So bigger number means you're more uncertain. So we started out with the value of 20, relatively uncertain. Now we have a value of 1.73. So we're having looked at the data, we're now more certain about where the value is. We've shifted where we think the value is, what sort of our peak credibility is, over to about 110, and we're much more certain now that it is there. And another sort of metric that's useful that people can report, or that you typically see reported, is the range from the 2.5 percentile to the 97.5 percentile. That's the 95% credible interval. It sort of reflects sort of where the bulk of your belief is in that parameter's true sort of population value. So we have those descriptors for the mu parameter, that's setting where the population's mean is. But we were also uncertain about the sigma, the variability of the population parameter, and so we get a posterior distribution on sigma. So it is centered on about 9.5. This is on the real scale and has a standard deviation of about 1.25. Credible interval from 7.41 to 12.31. And we can, so this is a numeric description of those distributions. We actually visualize those distributions. There's a function stan hist that we saw the other day, and we just give it the object out that we created, and this is the two parameters. So we get the posterior distribution. This is sort of the shape of what we should believe for this parameter mu. So centered sort of around 110. Most of the mass is between like 107 and 115. Ditto a posterior distribution for sigma. Got a peak here somewhere around like 9 to 10. But most of the mass is between, I don't know, 7 and 13. And if we actually look back at the numbers we used to create this fake data, the value 10 sort of fits nicely right in here. So this sigma distribution has actually captured the true value very nicely, and ditto, this mu distribution has captured this true mu of 110 quite nicely. Normally you wouldn't know these numbers ever. We're pretending to be God, generating the data, and then becoming human again and trying to estimate from the data. Had a question back here.
So we are giving the prior value and the past value, right? So but when we look at this value, so use it's actually the data we gave, like almost it is equivalent to the data we created, like the data we have, right?
It's close. I mean
the prior value doesn't have any impact on this one.
We chose relatively weakly informed priors. So what I mean by that is that the sort of variability we permitted on the priors was very large. Let's actually rerun it with these as being sort of super certain. So I'm going to say a normal distribution with a standard deviation of 1 there. And let's be similar. Let's say, I don't know, 0.1 here. So I need to resave that and then come back over here and recompile it. There's a way to make it so that you can actually include the specific values of your priors as data, in which case you don't need to recompile the model every time you want to try a new thing. I don't find myself tweaking priors so often that I need to do that, but that's a way to avoid the time waste of having to recompile the model. So what we're doing here is we are rerunning this sort of inference step where we have asserted that we are very confident in these priors. Now, again, we know the data because we are God and we generate the data with 1, 10, and 10. We know these priors are actually sort of not well suited to the data, or at least they are different from the data. So we should get some different results here. Okay, so it's compiled. I will run this. So double check again. Our hat is all 1. Effective sample size is all above 2,000 or above 1,000. But if we look at our values here, we've shifted to our mean has shifted away from 100, but only a little bit. It's about as wide. It's only reduced its width by a little bit. Remember, it was our prior had a standard deviation of 1. Ditto our mean for the or our prior on the or our posterior for the variability has shifted from the prior a little bit. It's reduced a little bit. It's actually gotten let's see, exp of 0.1 is 1.1. So it's actually gotten a little bit wider. So if you impose sort of really narrow priors, really certain priors on the data, you'll move a little bit towards the data, but not nearly as much as if you were sort of a little bit more uncertain about your data or about your priors.
Last class you said like we will get this prior from the previous studies on the research, but suppose we are studying something new.
Mm-hmm.
So what happens then? Like we don't know.
Okay, well, I was planning to show that in a different example, but now that you raise it, it actually does somewhat make sense to do it here. So what if we had some data coming in and we didn't have like a good sense of what, like the prior? A really standard thing is to scale your data before you do any inference on it. So what do I mean by that? I mean, let me go back to my R code and I'll make it bigger now. So we've got this thing Y. And it's all these numbers. We can do a these are again the actual numbers, or sorry, the data that we generated. And I can do a histogram of Y. So they go sort of from about 85 to 130. Does anybody remember what a Z score is? You take all the y's, or I'll let you actually try to answer. Anybody know? So, standardized score, is that familiar at all? Yeah.
Yeah,
So,
we use that for bonus.
okay, so what is a Z score?
I don't really know.
No? Okay.
But if you don't meet the cutoff,
So,
then you can use it.
so visually, what you could think of it as okay, let's take this distribution and let's shift it so that it's centered on 0, not this like 110-ish value. So we shift it to be centered on 0. So how do you do that? You say y equals, and I'm going to put this in parenthesis because we're going to have a second step here. So we say y minus the mean of y. That's going to pull this distribution so it's centered on 0, right? Okay?
One more time.
Yeah, okay. So if let me actually even just run this a little bit. So if I want to take this set of values and make it so that instead of going from 85 to 130, it's and with a mean of around like 110, if I want to make it so the mean's around a 0, but I guess that would make it negative 20 to positive. Well, let's actually just see. If I wanted the mean to be 0, I would just subtract the mean. I'd take all the values and I'd subtract the mean from it. So that's what this little bit does, is it says take all the values in y, and for each value, subtract from it this thing. This thing happens to be the mean of all the values. So having done that, I can say hist y. And now it shaped a little bit differently just because of how the bins were chosen, but now it's got a mean at 0.
You can see how much of an outlier something.
Yeah, well, not quite yet. Another thing that is useful to do, in addition to making it so that they're sort of centered on 0, you want to make it so that the range is about sort of some set. So you squish it together or pull it apart, depending on like. So this range is sort of from negative 20 to positive 20. What if I want it to be about like 3 to 3? I actually don't know if this is gonna. So you say y equals y, and instead of a subtraction, now you're going to do a division. So you're going to divide it by the standard deviation of y. So again, we're taking every element in y, and we're dividing it by this thing. And this thing happens to be this measure of variability of y. Standard deviation is a very common one to use. So what does that look like? Afterwards, well, so yeah, it makes it so that most of the data falls between negative 1 and 1. Some of the data falls outside of there. So this process of first subtracting the mean and then dividing by the standard deviation, that's called standardizing or Z-score. So now that we have this new thing y that sort of should have a mean of about 0 and should have a variability of about 1, or a standard deviation of, well, if you actually compute what the mean of y is, it's going to come out to being pretty much 0. The fact that it's not 0 just reflects that computers aren't great at storing really small decimals or doing an operation and making sure it comes out precisely 0. So that's basically 0. 9 to the power of or 9 times 10 to the power of negative 17. That's a lot of zeros before you get to numbers. So pretty much 0. And if we look at the standard deviation of y, it's 1. So we have this data now scaled, standardized. Oh, and I'll pull up my standardized so that it's pretty much centered on 0 and pretty much it's got a variability, standard deviation of 1. What we can do then is use what might be sort of termed standard priors, where we say, okay, I'm going to say the mean of the population generating this data has a mean of 0, and my certainty about where that is about 1. So what that means is that if I look at this data, I'd believe a value for the mean sort of anywhere pretty much within here. I mean, it would fall off on either side. If you wanted to be even less certain, you can say like put a value of like 2 over there. You wouldn't like a value of 10 would reflect like a fairly large. Like this is your variability in your sort of prior is 10 times more than than you observe sort of noise in the data. So that would be sort of really extreme. So 2 might be a reasonable value. And for this, so on the log scale, 0 is the same as a value of 1 on the real scale. And ditto that. Like 0 and 1 would be a relatively broad prior for the variability. So if you didn't have any experience with the domain of what the data is, you can rescale it and assert sort of pretty standard sets of priors on the sort of Z scores, and that's fairly sort of that's a lot easier to do when you don't have any prior experience with the domain. So does that sort of generally make sense? Yeah, question?
Isn't z-score like isn't z-score equal to the sample mean minus the population mean by the standard deviation?
Well, there might be different definitions of z-score in different contexts. So that definition implies that you know what the population mean is, for example, and if you're dealing with something like an IQ test that is pre-standardized in the way it's created, maybe you can make that assumption, but for this stuff, no, so I'm using a different definition, I guess, for the Z-score, which is just your
because in
scaling
this,
by the...
What I felt that was that you're using each value and then subtracting the mean. Like
yeah.
Each value of y minus the mean of all of the values.
Yes.
Of y.
Yeah.
Okay.
Yeah. Yeah.
Okay. So is that the same? Does that be the same? I mean, this is what I was thinking, that maybe it doesn't end up being the same thing.
Yeah, I don't think those are the same definitions. So I'm using Z-score to reflect that you've taken the samples and you subtract from them, each one, the mean of all the samples, and you've also divided each of the samples by the observed variability of the entire sample set. So there's nothing in here referring to the population at all. It's talking about each individual sample.
This will just work for normal distribution.
Okay, so if you so we haven't talked about other types of data. So if it's like binomial data or that sort of thing, then yeah, you're going to be less. This is not going to be a trick that you can use to set reasonable priors. But when we get to binomial, it'll be pretty clear how to set those. Or we'll talk about that more when we get to binomial. Yep.
Now that we scale the whole data like using Z-score, will we get like after like using all this data into the equation, will we get the equal like exact same number of mu and sigma?
Well, let's actually run it through. So having standardized y, we'll repackage it. And having changed these values, I'll have to repackage those, or I'll have to recompile the model. And to give you a preview, so we'll run it again through. Just waiting for it to compile. Ta-da. Okay. Can run it, and I'll rescale this. Okay, so looking first at the final columns, R hat 1, effective sample size above 1,000, great. Mu now, before it was like 110, now it's 0. Well, that's because we've rescaled things to be centered on 0, so it's estimating things. And it's got a variability of 0.19, and it's got a 95% credible interval from 0.37, negative 0.37 to positive 0.38. So that's this is a little bit of a problem insofar as the posterior is on the same scale as the prior, and the data, which is all on that Z scale. So if we want to refer back to the original scale of the data, we actually just, well, for the purposes of the mean, we can just add the mean of the original sample back to it. So that ends up being, what do you call it? That ends up being about 110 if the mean of the sample was about 110. The procedure for getting the variability back to, and so that the sort of range, so we can shift this up so that it's centered on 110, but the variability is still, the range is still going to be sort of incorrect. So we need to multiply by, I guess, each end by the standard deviation that we had in the first place. So let's actually do that. So we've got mean, well, so negative 0.37 times the standard deviation of, we got rid of y in the first place. Like we overwrote y as we did it. Happily, we presumably would have read this in from data somewhere, but I'll just rerun this bit to generate it again. So now we can say that, so I guess then we would have to say negative 0.37, we'd say mean of y, big Y. All right, so about 107 to, and it went to 0.38. So 107 to 114, and that actually was pretty much what the original thing had said. That's our super narrow prior, so we don't want to look at that. Yeah, 107 to 114. So you'll get the same results after centering and everything. There's actually some computational reasons to center when you can, but those only really matter when you have more complicated models than what we're dealing with. All right, so it's in the same way that it was so the first example we had was one sort of group, one sample, and we decided that it had a normal distribution, but we decided that we'd be uncertain about the mean of that population generating the data, but we weren't uncertain about the variability. We set it to 15. This time we had, again, one group. We were uncertain about now both the variability and the mean, but it's still a little bit of a kind of fake data set insofar as rarely are we ever interested in just one group. We usually sort of have some experiment and we're interested in comparing two groups. So that's what we're going to move on to next. So in my files, I'm going to go up to the, I'm going to skip to the 2 group one. So 0, 4, 2 group 1. And I'll make sure to set as working directory. I'll open up the R file. It's going to immediately, so I'll run a little bit at the top. It's going to remove anything that's in the working directory just in case. We've got some data generation here. Again, this section we're pretending to be God and creating some data with known population values, but then we're immediately going to forget those. So what it's doing, we're creating 2 sets of data, Y1 and Y2. We can look at what are sort of the general descriptors of these. Y1 has a mean of about 98. Mean of Y2 is a mean of about 109 or 110. And we might be interested in having seen these samples, so Y1 and Y2. Are these samples coming from the same distribution with a common mean or two different distributions? So we can look at the means of each one. They look like they're different, but we are not quite sure yet. So let's look at that stand file that's going to sort of express our model for the data. And I'm going to pull it out and over. So we're going to structure the data in the same way that we gave it a y and then another thing that told it how many elements in y there are. We're going to give it y1 and y2 and something that tells it how long y1 is and something that tells it how long y2 is. So that's the sort of structure of this data section. Let's look down at the model section. We've got y1 distributed as something and y2 distributed as something. So what's y1 distributed as? Well, it's normal with something called mu1 as its mean and something called sigma as its variability. And y2, it's normal with something called mu2 as its mean and something called sigma as its variability. So can anybody maybe translate that into English, into sort of a verbal expression of what our generative model is?
I'm probably horribly wrong. Y1 is normally distributed with a mean of mu1, which is again normally distributed in somewhere between.
Oh, don't worry about the just.
And a variance of sigma.
Okay, so maybe try to talk about the relation of y1 and y2. Like, what does the generative model say about any similarities or differences between how the data for y1 and y2 are being generated?
The same standard deviation.
Okay, so they're using the same thing, the same sort of named object here in the slot that for the normal distribution specifies what sort of how variable the distribution is. Yeah.
The standard deviation is more than 0.
Well, we're not going to talk about this yet, but yes, we have it set up like before where we are explicitly saying standard deviations have to be positive in the positive domain.
Both normally distributed.
They're both normally distributed. But they have different things here
Right.
for mu1 and mu2.
Potentially have different means.
Yeah. So that's the thing is that they could potentially, it could be the fact that mu1 will end up equaling mu2. But that's going to come out after we do our inference. Indeed, we actually will set out, so we say that there's a thing called mu1 that takes any value, a thing called mu2 that takes any value, and a thing called sigma that takes any positive value. Here, let's actually use that for sigma. Let's use that same distribution as we had before, log normal. That's better than Cauchy. I keep meaning to change these examples before class. So about 2.7, that puts it at a variability of 15 on the raw scale. And we previously decided about 2 there. Makes a nice shape. But for mu1 and mu2, they're both, we have a prior for both centered on 100, and variability, sort of, so an amount of certainty in that value, sort of as fairly, what was the phrase I said? Weakly informed. So fairly broad normal distributions, but peaked at 100 for both of them. So the prior actually is implicitly saying that there's no difference between these two groups at the outset, and we're going to update that prior with data and then ask, have these two is the posterior for these two means diverged, or have they stayed sort of centered on the same values? All right, so I'm going to save that because I changed what the prior was here. So I can go back. We can package the data for Stan. Again, passing it in y1 and y2, but also creating this sort of intermediary computation. That's the length of y1 and the length of y2. We will run this. Slightly different syntax here. It's going to look in the folder and find any file named .stan. I did that because I was making a lot of these files and I didn't want to keep typing the names in. So this should work if we double check now. It's in the right directory, so it's going to find this file and compile it. And similar to last time, I'm actually just going to take off a bunch of these lines so that we are just using the defaults. So we're passing it in our object, we're passing it in the data, and setting the seed. So it's compiled, we can run, and oops, I want to resize before I do this. All right, looking at our hat, they're all ones, great. Looking at effective sample size, they're all above 1,000, great. Now we can look at what's going on inside. So maybe let's first check that sigma column. We had a prior centered on 15. It's come out about 13, so it has been updated by the data. Standard deviation of 1, that's actually a lot less variable than our prior was. Our prior had a standard deviation of 2 on the log scale, which turns out to be 7 on the regular scale. So we're much more certain now that of where the sigma value for the population is. And we could describe it using the 95% credible interval, but let's skip to looking at mu1 and mu2. Have they diverged? Well, the mean of mu1 is now for our sort of the posterior distribution is now centered at around 98. So it started at 100, it's only moved a little bit down to 98, but the center of the posterior distribution on mu2 is now up to about 110. So that has shifted quite a bit. Both of them have narrowed from the variability of 20 in our prior. They've dropped down to about 2. And indeed, they've narrowed so much that they don't overlap with one another really in the 95% credible interval. So the 95% credible interval for mu1 is about 94, 94 to 103, whereas the 95% credible interval for mu2 is about 105 to 114. We can do a quick histogram of that. Stan hist out. And it's a little annoying that we can't sort of, well, if I did a little bit more work, I could make it so that these two were sort of on the same plot, and we'd see that they pretty much are just 2 independent peaks. But you can even see just from here, it's pretty clear they don't overlap by much, mu1 and mu2. So what would you, having seen this as the posterior distribution, so what you should believe about the 2 means, what would you decide about the question of whether they had the same mean, or whether it's tenable to hypothesize that they came from a population with the same mean? Well, the fact that they sort of 105 for this one is not very likely, and 105 for this one is not very, they don't have a lot of overlap. But it's actually a little bit difficult to see and think about as these 2 different. It's better to, when you have a scenario like this, or well, whenever you're talking about an effect, whether there's a difference between 2 things, instead of sort of structuring your model so that there's a parameter that has one thing and parameter of the other thing, it's a lot easier to think about it in terms of a parameter that sets how big the difference between the two things are, and then another parameter that sets sort of where their center is. And that way, you can have a posterior distribution that specifically talks about the question you're interested in, which is how credible are different values for the difference between these two things. So the next example shows that. So this example is simply to sort of get you warmed up for the idea of two groups potentially differing in their mean. The next one's going to be structured exactly the same in terms of the data generation, but is going to be slightly different in how the model is structured. So we'll go to 505 to group 2. Set the working directory here. I'll close this file. I don't need to save. And open up the R file. First little bit again just clears the working directory. The data is being generated exactly the same as before and packaged exactly the same as before. I'm gonna go look at the stand file that's associated with this, and I'll pull it out to its own window. So data's coming in exactly as before, but our model section is gonna look slightly different. Now, I mean, we can even glance through here and see that we've got a different sort of set of parameters. But let's start with down here. So y1 is distributed as a normal distribution. Again, it's got a variability thing called sigma. But now instead of something just called mu1, we're saying mu plus diff. And we're saying diff divided by 2. You actually don't need the divide by 2. You just would need to remember to divide by 2 in the posterior. But here we'll be explicit that if you imagine that there's some mean that's maybe common to, or there's some center between these two distributions. Maybe there are IQs, and so the center is somewhere up around 100, and one's a bit bigger than 100, and one's a bit smaller than 100. So mu defines on where the center of the two groups are, and diff defines what the difference between the two groups are. So whenever you have two numbers, you always need two numbers to define them. One way could be what's the value for this number and what's the value for this other number. The other way is what's the center between the two numbers and what's the distance between the two numbers. So it's this center distance form that we're going to use here, and that allows us to talk directly about the thing that we're interested in usually, which is the distance, the difference between the two. So mu is again the center of the two groups. If the two groups are the same, the center is going to be their same common mean. And diff is the distance between the two groups. Again, if the two groups are the same, then the diff should be centered on 0. It should be about 0. So mu could take any number. Diff can take any number. And sigma, it's a variability parameter, so it has to be bounded at 0. In terms of priors for these values, and critically, y1 is mu plus the difference, and y2 is mu minus the difference. One has to be plus the difference, and the other has to be minus the difference. It actually doesn't matter which one you put plus and minus in front of, just as long as one is plus and one is minus. Sigma, again, we'll change this to log normal, 2.7 and 2.
Why is divided by 2?
So that, again, we're starting at the center and we're adding some amount of, we're adding some value to get to the next, to get to the one on the right. So we have to take the distance and divide by 2 to get from the center to the thing on the right and the center to the thing on the left. So that's why it's divided by 2, because you're starting in the center and moving half of the difference to get to one of them, and starting in the center and moving half of the difference to get to the other one. So what's nice about this parameterization, you can talk about the center where it's located, and we were just using this, okay, generally assuming they're starting at 100, but having this weak prior on it of about 20. But now we can have a prior directly on the difference. And whereas before the model had, where we had two, I actually think I might still have it open. Yeah, we had two mu's, mu1, mu2, and we had them both as a prior centered on 100. And that established what would be called an implicit prior of a difference of 0. Now we're being explicit. Now we can be explicit about that difference between the two groups as being 0, and we can actually choose whatever prior for that difference we want. Maybe we're really certain it's 0, but we're uncertain as to where their common mean is. Or maybe we're really certain as to where the common mean is, so 3, but we're rather uncertain about whether there's a difference at all. So you can independently sort of set the priors for those. We're going to put them as both sort of the same sort of degree of certainty, at about 20 on the IQ scale. Again, we could have standardized this scores, and then that would have mean that we would have that as 0, and sort of that as maybe 2, and that as maybe 2, etc. I'll leave it as on the IQ scale. So having set these, I'm going to save because I changed this bit a little bit since I opened. So does that, before I move to talking about the data, does this generative model, it's the exact same data as the previous model, but we have changed how we're talking about it. That makes it easier to talk about the thing that we're interested in, which is the difference between the two groups. So having done that, I can come back in here and tell this to, well, check my working directory. Yep, 05. I will run and get rid of some of this stuff to just have the defaults, which pan out well for this. I'm going to change the size of this so that when it prints, it looks good. Waiting for the model to compile. This is a slightly slower machine than I've had on previous days, so the models are compiling less rapid. But there we go. It's run. We look at our hat, all ones, effective sample size, all above 1,000. So we can look in here. Now instead of mu1, mu2, sigma, we've got mu diff sigma. Sigma should turn out to be the same as before, about 13, with the same small, now more confident posterior spread. Mu is now defining the center point between the two distributions. So it's actually not super interesting as a parameter to look at. We can note that we started out at 100. It's moved a little bit. And its variability started out at about 20. Now it's narrowed, so we're more confident about where it is. But critically, the difference between these two distributions now is the thing sort of we might be most interested in as sort of people that did some experiment and collected data and wants to know if there's an effect of our experimental manipulation. So we can see now that there's a distribution. We had our prior centered at 0 with a spread of 20. Now it's centered at about 11, and its spread is about 3. The credible interval is from negative 17.9 to about negative 5. If we did a quick histogram of all those, stan hist out, it'll show the posterior distributions for all our parameters. So there's mu, there's sigma, and most critically, our difference distributions. So if you were an experimentalist, you'd just done some costly experiment and you want to do inference on whether the manipulation worked, what would you decide on the basis, and I'll give you a hint, it's this histogram that you want to be looking at. So what is a hypothesis that's typically of interest in, again, every value on the x-axis sort of represents a possible value for the parameter in the population. What's a hypothesis that's particularly of interest when we're doing experiments? A value on this axis. Okay, 0. So we'll look directly at this axis, look for the value 0. So 0 means there was no difference. How credible is 0 in our posterior distribution? So there's not a lot of data near 0. There's not a lot of samples from our posterior near 0. If we were to have like a nice smooth curve, the curve wouldn't be very high there. Equivalently, like you can actually, in some scenarios, establish a region around 0 that you sort of will treat as equivalent to 0. So a 5-point IQ difference might be not very, like even if I were confident that there were a 5-point IQ difference between two groups, I might not treat that as, say, clinically significant. So in a lot of domains, particularly medicine and medical treatments, there are sort of pre-established norms for what people consider sort of clinically significant. So if I were to have that sort of predefined range, you could even talk about how credible is sort of beliefs in that entire range. If you're 95% correct, so one sort of decision strategy, and this is after you're doing the Bayesian thing, if you want to try to, one way of summarizing your beliefs is actually showing the distribution and maybe a numeric representation of some of the descriptors, so the mean and the variability and the 95% credible interval. But after that, when you're writing your discussion, you have to sort of give people some recommendations as to whether to move forward with this treatment, for example. And one decision strategy that people can use is to simply ask, does the 95% credible interval exclude 0? In which case, you might decide that yes, the thing works, there is a true difference. If you have the scenario where you have sort of a region where you consider all those values pretty much 0, an acronym for this is ROPE, Region of Practical Equivalence. Then you might try to have the more sort of stringent criterion that you want your 95% credible interval to completely fall outside the region of practical equivalence, the ROPE. When you have a region of practical equivalence, you actually have a nice scenario that you would never encounter in the frequentist world, whereby you can ask, you can have the scenario where if there is sort of pretty much, if you've got a lot of data suggesting there is no difference, you can have the scenario whereby the entire credible interval falls within your region of practical equivalence, in which case you'd be very confident that there's no sort of practical effect happening here. So typically that's, it's very frowned upon in the frequentist world to talk about sort of, I've proven the null, or I've sort of strongly supported the null, even though that technically is a thing in sort of the Neyman-Pearson decision framework. Here in Bayesian world, that's totally possible to do. You can totally express confidence that there's no effect. Yeah. Let me actually just do a quick check on, I didn't think I'd get through this part this quickly, so I'm going to check what the next one, that was 5. Let's check the model here. Okay, well, so the next two, so in the same way that 0, 5 was the same data, two groups, they're going to have a model where there's two groups, they differ just by the mean they have, they're going to have the same variance. We can have a different but we had a different way of arranging the way the model was structured, such that we had in one mu1 and mu2, and the other we had mu and a difference. 06. So I'm going to go to this folder 06. I'm going to set as the working directory. Make this plot go away. Here's the stand file. I'm going to close the R file 405. Open up the R file 406. At the top of the R file for 06, it deletes everything. Stand's already loaded. We don't need to run that. It runs. It creates this data again. It's actually going to be the same data. But we're actually going to structure it slightly differently. Before, we just had this thing y1, and it had all those values, and y2, and it had all the values. We're actually going to put this in a data frame this time. Often, this is how data come in. So I'm just going to run this and show you what it looks like. You don't really need to know how this is structured. So let's just look at what my long data looks like. My long data. So this is a data frame, so it's going to print out everything. Okay, so we've got this thing. It's a data frame. It's got 3 columns: Y, group, and this thing called X. So Y is the measure that we have for each individual, and group is a label that we have for each individual, whether it's in group A or group B. So the exact same thing as before. We had y1 as an object and y2 as an object. Now we've got a single object as a data frame with 2 columns. The one column codes the sort of data point, or the value for that individual, and the other point codes what group that individual was in. This is a lot more common to have as a data format. This is called long data. That's why it's actually called long data. My long data but yeah, the structure of this data where you have a case per line. Actually, technically, this isn't long data. This is neither long nor wide. There's 2 different types of data, long and wide. Wide typically is a case per line and multiple descriptors for that case along the line, or possibly multiple data points for that case along the line. Long data can allow the same sort of person have lots of lines, but in this scenario, a person has 1 descriptor and 1 data point, so it's neither long nor wide. So you can ignore the name here. It's a bit of a misnomer. But say you had read this in from a data file. It's the same fundamental sort of model, though, as you want for the data. You want to you have 2 groups of observations. We want to model them as having some as being normally distributed. Each group is normally distributed with the same variability each, but possibly with a different mean, and ideally using that center and distance parameterization rather than a 2 means parameterization. So let's take a look at our stand file. So the stand file wants us to, and I'll pull it out so it's bigger. And I'll scroll up. Okay, so the stand file, it's ny. This is going to be the total number of observations across both groups. So if I flip over to my R code, when I'm packaging up the data, I'm going to say ny equals, and use the nrow command. That counts the number of lines in this data frame. Y is going to be a vector of observations of length ny. X is a vector of predictors. And notice I've got these 3 columns in the data frame, Y, group, and X. Every time you see an A as group, X is being negative 0.5. And every time you see B as the group, you see positive 0.5. So I've actually hand-coded that in. there's a really easy way to do that, but I'll save that to next class to show you that. But these are these numbers reflect like how much you'd need to move from the center to get to one group and how much you'd need to move to the center to get to the other group. So you need to move half of whatever diff parameter we're going to get to this group and half the diff parameter in the other direction to get to this group. So that's where that x comes from. The parameter section is going to look exactly the same as before. We have mu, which is going to be the center between the two groups, diff, which is the sort of amount of different distance between the two groups, and sigma, which is the amount of variability within each group. And the priors for those three are going to look the same. The only thing that's going to look different now is that instead of having y1 is distributed as and y2 is distributed as, we have a single statement here saying y is distributed as, and we have a normal distribution, same as before, variability of sigma, which is the same as before, but now we've got this equation here defining how to compute the different distances. And critically, it's saying the distance, or I guess the result that it computes here, mu plus diff, is going to be dependent on what the value of x is. So x is data coming in, and x is that either positive 0.5 for one group or negative 0.5 for the other group. So this is functionally similar to having the scenario where you've got y1 and saying plus diff divided by 2 and y2 minus diff divided by 2, except the plus diff and minus diff, that's all being put into one sort of line here. So again, this is the exact same data type, data scenario, exact same model, generative model for it. We've just been able to actually simplify it a bit by having the data coming in this specific structure, and now we can just say diff times x. This is going to be the sort of better way to structure things, because when we get into more complicated models with multiple predictors, it's a lot easier to give it just a vector of predictors and have that vector here rather than having to assign each sort of subgroup of the predictors to its own y. But I'll go back through this example as we start the next class and get into more complicated examples that class too. Any questions on today's material so far? No? All right.